Are you ready for the range, which most people love ranges, and the standard deviation, which is also a thumbs up because I love standard deviation. You might not like standard deviation, but we'll see. So we're going to start by looking at some quiz scores, some data sets. They're made up. They're not your quiz scores. Good thing too, because your quizzes are out of 20 points. And again, remember what we did to start this week. Centers, means, medians, and modes are all different ways to talk about the center of data. Well, now we're talking about how to show the variation, because all three of these sections have the same median and mean. Okay? They all have the same median and mean. They all have a median and mean of 5, but there's different variation, right? This first section, they all got the same score. The second section, everyone either aced it or didn't. And the third section, everyone did bad. All right, everyone did about the middle, an F. Okay, so right, this one has no variation. This one has a ton of variation, right? There's zeros and tens all around. This one doesn't have very much variation. They're all pretty similar, but more variation than section A. Okay, so that's what we're going to talk about. We're going to talk about range. That is one measure of the variation here, and standard deviation, which is a very common one. So the range, all the range is just the difference between the maximum value and the minimum value. You may have also heard range in algebra. Range is the set of all outputs of a function. That's a different range. Okay, forget your algebra. That will be a happy thing for some of you. Forget your algebra. Range here in the context of statistics means something different. It's the maximum value minus the minimum value. There are some similarities between the two definitions, but they're not the same thing. So let's go back to the price of peanut butter, a jar of peanut butter. So find the range of this data set. So find the biggest. We found that earlier. Find the smallest. That's right here. And the range is just the difference between these. So the range here is going to be $3.99 minus $3.29, which is equal to 70 cents. That's not where the decimal place goes. Nice try, Jason. So the difference between the cheapest and the most expensive jar of peanut butter here is 70 cents. That's going to be our answer. The difference in cost between the most expensive and cheapest, I'm going to make up a new word, uncheapest jar of peanut butter is 70 cents. What's the cent sign? Is it like something like this or something? Am I making up symbols? You can write $0.7 as well. I think it's something like that. All right. That's our answer here. That's the range. So what's the range here? The difference between the highest and the lowest value. Range here is 0. Range here is 10. Range here is 2. And again, if you don't feel like sorting the data, right? It's hard to find the difference between the highest and lowest data values if they're not sorted. If you don't want to sort the data, you can just use GeoGebra and look at the difference between the minimum and the maximum. So in this other problem, you would just take 138, subtract 85, and you'd find the range that way. So that's relatively straightforward. Now we're going to talk about the standard deviation, okay? There's a lot to say here. So the standard deviation, I'm going to switch over here so I can just write with my pen. This is pronounced sigma. It is another Greek letter. Sigma is the standard deviation, and it's a measure of variation. That's why it's in this video. And it's based on how far each data value deviates or is different from the mean. So if there's a lot of values that are different from the mean, the standard deviation is going to be big. If there's not a lot of values different from the mean, the standard deviation is going to be small. So before we even introduce it, here, no data values deviate from the mean. The standard deviation here is 0. because nothing deviates from the mean. Here, the mean is 5. Zeros and 10s are both really far away from the mean here, as far away as you can go for a quiz score. So here the standard deviation is going to be big. I don't know what it is off the top of my head. I would have to calculate it. And here, there's only small standard deviations. There's only small deviations from the mean. The standard deviation is going to be a small number, but it's not going to be 0 because the 6s and the 4s are different from the mean, which was 5. Excuse me. So let's look at a couple of things about the standard deviation. So the standard deviation is always positive or 0. Remember, 0 is not technically positive. It is 0 if all of the data values are equal. And it's going to get larger as the data gets more and more spread out, kind of like we talked about with those quiz scores on the top of this page. It also has the same units as the original data. So if we calculated the standard deviation right here, the standard deviation would be in dollars and cents. Don't forget the units here. And just like the mean, it can be highly influenced by outliers. So if there are a bunch of outliers, or if we have really skewed data, a lot of times we talk about something called the interquartile range. I don't remember whether we're including that in a video. Stay tuned. And finally, you can think of this as like the average. Like most of the data is the average, otherwise known as the mean, give or take the standard deviation. In stats, we talk about if something's normally distributed, and a lot, like bell curve, and a lot of things are normally distributed, then like 68% of the data is within a standard deviation of the mean. But here we can just kind of think that, yeah, more than half, quite a few things are usually within a standard deviation. This is not a hard and fast rule. Okay, it's just a way to kind of think about the deviation. Think about what standard deviation means, because it's a little hard to visualize it outside of that. So we got good news and bad news for how to calculate it. You want a step-by-step process? I got a step-by-step process for you. Okay, but I'm also allowing you to use your computers. So before we even look at how to calculate the standard deviation, it's right here. Sigma and S. They're slightly different. We'll talk about when to use which one. It's a bit of a confusing thing. It's kind of weird. But GeoGebra can calculate your standard deviation just right there for you. But let's go about doing it by hand. One of the easiest ways to do it by hand, and you do not have to do it by hand. October, don't you dare scratch on my bed. One of the easiest ways to calculate the standard deviation by hand is to organize the data in a table, just like we have right here. Okay, so excuse you, I'm in the middle of a math video. So we're gonna just look at all this stuff and look at these prices. We're going to write all the prices down, and we're going to calculate the mean and this other stuff. Where this comes from is not super important, but let's just get going. All right, if my cat will let us. So here's our 5 jars. Okay, so what we're going to do is add up all of these jars with a calculator. And again, we can go and take our calculator and say, what is 329 plus 359 plus 375 plus 379 plus 399? We find that the sum of all of these is 18.41. This is the cost of buying all these jars of peanut butter. Well, then what's the mean? The mean is that sum divided by n. N equals 5. If we divide this by 5, we're just filling in this whole table, and we're going to eventually get to the standard deviation. The standard deviation is this last box. Nope, that's not true. The variance is this last box, otherwise known as sigma squared. Actually, this is not even the variance. we use the last box. We use the last box to come up with the variance, which we haven't introduced yet. You know, maybe, all right. I didn't want to go through this, but it's going to be more helpful if I do, right? So we're going to start by finding the deviation from the mean for each data point. So for each data value, we're going to subtract the mean from that data value and say, okay, each of these jars of peanut butter, how far are each of these from the mean? Now we want to talk about the distance. How far a distance from the mean? We want it to be positive. So we could take the absolute value, but the absolute value is kind of a weird thing. So instead, what we're going to do, this is our step one, we're going to square it. Squaring it's another way to make something positive. We're going to square those, and then we're going to add them all up. We add them all up. This is step 3. It's right there. Once we add them all up. So the table is just getting us to complete step 3. And then we'll either divide by n or n minus 1. And it depends on whether the data set's a sample or from the whole population. Okay, so you can just assume that most things are going to be a sample, but some things are going to be populations. So sigma, this is important to write down. Sigma is the population standard deviation, and here we divide by n. The notes are using capital N. I usually see it as lowercase n, but you can use either one. And then S is what's known as the standard deviation for a sample. We call it the sample standard deviation, and we'll divide by n minus 1. And we can assume that if we don't know which one it is, we're just going to divide by n minus 1. If we don't know, we'll assume a sample is given. So we're assuming this is a sample right here, for example. Okay, so let's get tabling. We found the mean to be this sum divided by how many there are. The mean is 3.682. And the mean is the same for all of these. The mean is always 3.682. We don't really have to fill this in. This is not important. You could fill it in if you want. So now for each of these data values, right? This is step 1. Find the difference between the data value and the mean. Take the data value and subtract the mean. So it's 329 minus this value. 329 minus 3.682. That's negative 0.392. And you do the same for all of these. Okay, 359 minus the mean. That's going to be negative 0.092. 375 minus the mean. You can see why I love using computers for this, because this is getting very tedious, right? And we only have 5 data points. So most of the time, and immediately after I finish this example, I'm going to show you how to do it with a computer. You can also use your calculator. You can also do other things as well. And again, this sum is not important either. You could calculate it if you want it. Now we have to square. This is step 2. Square each deviation. So we just take everything here. We need to square this value and see what it is. All right, so squaring it's going to turn it positive. We have 0.392 squared. That's going to be approximately, oh, let's write out all the digits. If we're already going to be tedious, let's be extra tedious. 153,664. And then we just do all of these again. Wow, isn't this fun? Isn't math fun? I'll tell you what, math is a lot more fun when you can use computers. One advantage that you guys have over people from my generation. 0.004624. Actually, some of you are from my generation, and some of you are from different generations. And I need to finish this problem so I stop talking. So we're just squaring each of the data values to the left, typing it onto a calculator, and recording these. So notice, by the way, which of these numbers are the biggest? The biggest is the one that's the furthest away from the mean. This 329 is the furthest away from the mean. This is contributing the most to our standard deviation. And then we finally add up all of these values. So it's 0.153664 plus 0.008464 plus 0.004624 plus 0.0. Just adding up all of these values. And that's what goes in the bottom. This is our step 3. We've finally done step 3. So that's the hard part. Filling in this table is very tedious. You don't actually have to do it by hand, but this is how you do it by hand. Okay, add these all up, and then step 4 is the weird one. If this is a population, we divide by n. If this is a sample, we divide by n minus 1. And it didn't tell us, so we're going to assume sample. So the variance is what this step 4 is. A lot of times it's called sigma squared. It's known as the variance. Is going to be this sum, 0.27328, divided by n. Actually, so it's a lot of times called sigma squared, but that's only for the population. Here, it's s squared, right? Because our standard deviation is s. Our sample population, our sample standard deviation is s, so our sample variance is s squared. That's going to be divided by n minus 1. N equals 5, so we're dividing by 5 minus 1, or 4. Type that all in. Really hope I'm not making a simple algebra error here, arithmetical error, because there's a lot of ways to make silly errors here. And we get this as our variance. And step 5, compute the square root of the result. The square root of the variance is our standard deviation. It is s. That's going to be the square root of this value, which is going to be something. 0.26 approximately. And remember that our standard deviation has the same units as the data. So 26 cents. That's our standard deviation. So on average, an average jar of peanut butter is $3.68. And most of the jars of peanut butter are going to be within 26 cents of that. Okay, so that's, if you wanted to interpret your answer, you'd say most jars of peanut butter are within, kind of just a rule of thumb, 26 cents. However you can write cents, I don't know how to write cents, of the mean, which is $3.68. Okay. But you don't have to interpret the standard deviation, because this is not even true for every problem. Just a good way of thinking about it, a good rule of thumb. Okay. There's another way of doing this. You can use GeoGebra. Type in your data values into GeoGebra. 329, 359, 375, 379, 399. Highlight them like this, or click on the whole column. Click up here, one variable analysis. That creates a histogram. Show statistics. S is our sample standard deviation. Sigma is the population. We want S here. 0.2614, or about 26 cents. A little faster if you use a computer. Okay, so feel free to use a computer for all of your standard deviation calculations. All right. We didn't actually need to find it, but if we wanted to know the standard deviation for the weights of the models, you'd go over here and do the same thing. The standard deviation of the weights of the models is 16.9 pounds approximately. Okay. Remember, use S. This is the value when you divide by n minus 1. Use S for samples, which is going to be most things for us. We only use sigma. We only divide by n And there's a long story for why this is the case. We use sigma for the population standard deviation. Remember the difference between population and sample? Population is the whole group that we're curious about. Sample is a small portion of that group that we are actually able to ask. Good luck. Hope you enjoyed that 20-minute video. I'm sorry, that's too long. Bye-bye.